The broadcast is now starting. All attendees are in listen-only mode.
Welcome to our webinar, Effective HALT Testing Webinar. Thank you for joining us. This webinar is being given by MET Laboratories. MET is a leader in the testing of electrical and electronic equipment for environmental hardiness, product safety, and electromagnetic compatibility. MET operates world-class labs in Baltimore, Maryland, Santa Clara in Union City, California, Austin, Texas, and also runs operations in China, Taiwan, and Korea. This webinar will run 30 to 45 minutes with an additional 15 minutes for questions and answers. Due to the number of registrants, all attendees will have their phones muted. If you have a question, please type it in the questions area of your GoToWebinar control panel. We will attempt to answer all questions at the end. Just a quick note on other upcoming events. We're hosting a CB Scheme webinar on April 7th and a North America Product Safety Certification webinar April 14th, and you can go online for more information. Today's webinar is being presented by Tamlin Franklin. Tamlin is MET's Test Engineering Consultant, and at this point I will hand over the presentation to Tamlin.
Thank you all so much for joining us today for this webinar. What this webinar is supposed to do today is to provide an introduction to the beginner HALT tester and also to describe why it's necessary, some of the benefits, and if you are interested in the process, then we would want to cover all of the things that would be required before you actually come into the lab. So we'll wrap up the presentation with what it takes to be prepared to test for HALT and to test effectively. Again, thank you so much for being with us. I'm not sure how many people on the line are actual test engineers, project engineers, or design engineers, but we know that with every company, no matter what your role in the company, the success of your company really depends on the product and the reliability of the products that are produced. We know from experience in the test field that warranty returns, they can cost companies millions of dollars. And warranty returns are usually the result of some design flaw that wasn't found before the product was released. So what happens with the company is that your reputation may suffer. It may cost you millions of dollars. It could cost you personnel. It could be very costly to the company. So finding those faults and failures with the products that you produce, they can sometimes take months, and that's the reason why the product release dates are pushed out farther and farther. So for all these reasons, HALT came into play. And it really is a manufacturer's and a design engineer's dream. Because in the past, when reliability testing was introduced, it was really based on military specifications, and oftentimes the mil specs were based on field data to find design flaws. And we know that mil specs can be limited because, for one, they don't test products outside of their limits, and secondly, they don't necessarily find design flaws. And in traditional testing, we know that we never test outside of the limits. That is the forbidden zone. So if a failure is found outside of the limits, what we normally hear folks say is that, oh, that doesn't matter because it was outside of the limits. Now, in HALT, when it was introduced in the 1980s, the same failures that were found outside of the limits were now being addressed, and the root cause of those failures are found. So HALT is a process. It's not a pass or fail test. It is a process, and it requires a mind shift. It requires a new paradigm, a new way of thinking, because it's not the traditional testing that is required by many specifications. oftentimes we want to pass the test, as I said a few minutes ago, but now we have to have the attitude of wanting to find problems. So HALT is really a process where we are looking for problems. The process generally takes 2 to 5 days, whereas in traditional testing, finding design weaknesses or flaws could take hundreds or thousands of hours, which equated to weeks and months of testing. Now, HALT, the acronym stands for Highly Accelerated Life Test. And again, it's not a test, yet it's a process that is designed to help the design engineers or others who are involved with the design process of a product. It is designed to help those individuals find the weaknesses in a product design before the product goes to market. It is designed to help companies introduce products to the field that are more reliable, more robust, and products that will limit the warranty returns for companies. HALT is designed to stimulate the product versus simulating some traditional environment. Again, it's not a pass or fail test. With HALT, the product is operational and monitored throughout the process. And in HALT, when we find failures, failures equate to success in HALT. Now we take the HALT data and we use the limits that we find in HALT to develop a highly accelerated stress screen, which is the other acronym that you see on the screen now, HAS. And HAS is basically used for production of the product so that we limit the number of units sent or shipped to the field that may have process or manufacturing process issues. Now, many types of products can undergo the HALT process, and some are included here, but of course this list is not all inclusive. And again, we're saying that HALT is a process, so it's not a test just for one type of equipment. It's for every type of equipment that requires some engineering prowess. HALT is not viewed as a pass or fail test, so I'm trying to get your mind to shift from traditional thinking. When we think of testing, we think of traditional testing where the product has to pass or fail. In HALT, we are looking for failures before the product is sent for the last stage of production. The product types that can undergo HALT, again, are listed on the screen, but again, it's not all inclusive. We can test down to the circuit board level, subassembly levels, such as power supplies or card cages. We can test box or rack assemblies or subassemblies, and also at the total system level. So there are no limits with products that can be subjected to the HALT process. The equipment that is used for HALT is shown on the screen, and there are some variations from lab to lab with the chamber, but the basics are the same. The chamber utilizes liquid nitrogen and allows the product to achieve very rapid ramp rates, up to 60 degrees C per minute on the product. The chamber also uses pneumatic hammers, which provides a multi-axis vibration in all degrees, in all axes, in all rotations simultaneously. And the frequency band is rather extensive as well, from 10 to about 5,000 hertz, and up to 10,000 in some cases. The chamber is equipped with 2 access doors, an access port. The access port is here, windows to see the product while it's under test, and this is just a control for the chamber. But the doors are on both sides, and it allows easy access for mounting the product for testing. Here's an interior view of the chamber, and you can see that there is a table that has 3/8 inch hole patterns on 4-inch centers. Again, there are 2 doors for easy access, so you're not limited to which side of the chamber you can access. The chamber interior dimensions are 36 inches wide by 36 inches deep by 37 inches high. So that will pretty much indicate what size product can be tested. But if the product is too large, then it can be broken down into the circuit board level or subassembly, as I talked about on the previous slide. And I spoke a little bit about the vibration. It is a random vibration, and it's different from electrodynamic shakers. It's a multi-axis vibration, 6 degrees of freedom simultaneously across a large frequency band. The chamber operates pneumatically driven hammers, which generates a pulses, and that's how we get the random vibration. And some folks may say, well, why this type of vibration? Well, it's been proven with HALT over many, many years now, since its inception in the early 1980s, that the same defects found with temperature or power cycling in traditional testing, which may have taken hours, the same defects can be found using vibration in HALT in seconds. And some of those failures were bad solder joints. So HALT has allowed customers to find problems that has taken hours and hours of testing to find in a matter of seconds. And the random vibration, I guess I should say that while it is repeatable, it does not give the same vibration spectrum each time, although the vibration is repeatable. Now, some reasons why HALT is very beneficial. You may say, well, why should I test my product outside of its limits? It will never see those extremes. Well, when the product is tested outside of the limits, we have an opportunity to evaluate the failures and find the root cause of those failures, which will give you better understanding of your product and maybe make some minor changes before the product goes to market. So instead of spending hundreds of hours, and in some cases thousands, you can quickly, and I do mean quickly, 2 to 5 days is quick in the testing realm. You can take 2 to 5 days to discover the design and process flaws with your product. This short time reduces development costs, and if you're trying to meet some product release deadlines, the product in some cases may not be ready. And HALT can become an option for you because it will allow you to eliminate design and process problems again before you release a product for manufacturing. So one of the major benefits is you are able to get your product to market sooner rather than later when you incorporate the HALT process. Pardon. I love this next slide because a picture really is worth 1,000 words. Now, a company showed with the use of the HALT process how they were able to save a substantial amount of money. So when they first found the product, they found a weakness in the design phase, which was very low cost. But if the same failure was not found and the product went to the next phase in the production, then that same problem, you see the costs are going up. And if you don't catch the problem before the product is shipped, look at how the costs are increasing. And you can see a very small problem that could have been found in the design phase of a product has now cost a customer close to $1 million because they didn't find the root cause of the problem and make changes to the product before the product was shipped. Now this first illustration shows the product development using traditional methods. Now we're plotting spending versus time, and at each stage at each design stage, there is some verification testing. So initially, there are some costs associated with testing that ramp up relatively quickly. And then at each stage, you have to test, and then there are no trouble found, and so on and so forth. And at the last design verification test, the product is ready for release. Now, when the product is released, you see that the rate in spending kind of drops until we get down here to around month 18. And this is not an actual time for a specific product. This is just for example purposes. Around the 18th month, you see an increase in spending. Now, this is for the field failures that occur in the product. Now, we have to use personnel to find out what the problems are, and manpower is used, and that's what this blip here comes from. Now, there can be many more of these, and they could actually be higher depending on the product. Now, with the introduction of HALT, we can see that the same product, initially there will be some testing, and the cost will ramp up relatively quickly, but before the last design verification test is completed, HALT is introduced, and that's what represents this additional spending here. But you can see after HALT was introduced, the manufacturer's release date was actually moved up. The product was released sooner, and you can see the significant drop in spending after HALT was released. And there's pretty much a flat line with spending after the introduction of HALT. Now again, a picture is worth 1,000 words. So the savings that are recognized here are as a result of the introducing HALT before the product was released. Now, what is involved with the HALT process? Well, the HALT process includes test plan development, where the HALT engineer or the MET engineer would work with your company to decide what constitutes a failure, what kind of equipment will be necessary when you bring your product in for HALT, what type of ancillary equipment will be necessary, how will we verify functionality, because again, the product is fully operational and it will be monitored throughout the process. Then once we actually start the process, then failure analysis would be done at the customer site. So a root cause analysis of every failure found, no matter what extreme those failures were found, should be investigated, and then corrective action should be made. So it's the manufacturer or companies, the onus is on the company to make corrective action. And if corrective action is foregone, then on the previous slide when we showed a $35 fix resulting in almost $1 million worth of additional costs, you can see the rationale for incorporating the process. And then once corrective action is made or implemented, then the HALT process would be repeated to make sure that no new anomalies or weaknesses were introduced to the product. And then there would just be ongoing evaluation. So you may bring the product in just for a one-day evaluation just to see if what you have incorporated really is substantial and really is worth continuing on with the process. Now, HALT is a step-stress process. The process is repeatable, and basically it involves step stressing in a simple process in an incremental fashion where we dwell and increment after a dwell at the previous step. So this process is used for both temperature and vibration, they're increased individually first, and then the final step in the process would incorporate temperature and vibration in a combined environment. So to test effectively, other stresses should be incorporated as well, such as power margining, load margining, frequency margining, clock frequency, component value variation, voltage input. I mean, the list can go on. Pressure margining. Whatever your product function is, we would want to add additional stresses in addition to the temperature and vibration extremes that HALT provides. The temperature dwell at each extreme is really predicated on the size and weight of the product. So if a product is relatively small and lightweight, then the dwell may be a lot shorter than a product with more mass. So a typical dwell is 10 to 20 minutes, but for smaller products, the dwell may be 5 minutes at each temperature extreme, and for larger products, the dwell may be longer than 20 minutes, just enough time for the product to stabilize at the temperature or vibration extreme. The test stress levels are increased until the operating and destruct limits are found at each stress. Now, the operating limit of a product is basically defined as, say we are testing a product at 10 degrees C for level A, 20 degrees C for B, 30, 40, and 50 for E, right? Now, if we are testing a product and no anomalies are found as we step up and dwell and test the product and ensure that the product is operating or functioning properly, no anomalies are found until we reach 60 degrees C at level F. Now, at 60 degrees C, we back off the temperature and the product recovers at 50 degrees C. Well, 50 degrees C would be considered our operating limit. It's the point prior to any anomalies being observed on the product. Now, the destruct limit would be if we tested up to 50 and found the operating limit, we wouldn't stop there. We would continue on until we found the destruct limit. Now, if we tested at 60 and the product never recovered, then 60 would be considered our destruct limit. I hope that was clear. If not, I'm sure I will get a few questions about that. In HALT, everything imaginable is done in order to force failure. Because again, in HALT, failures are successes. So if you make it through the HALT process the first time you've ever tried it and no failures were found, well, we wouldn't consider that a successful process. However, if you have made changes to your product and incorporated the process and you come into the lab and you don't find any weaknesses, then that would give you a vote of confidence on your product, ensuring that the changes that you made and seeing that there were no failures found, well, then that would give you confidence in the process. But if you have a brand new product and you come into the lab and you're really, really nervous and biting your nails because you're not sure if the product will succeed or be successful outside of its normal limits, and your fingers are crossed and you make it through the test program and no failures are found, well, that wouldn't be considered a successful HALT because we're looking to find weaknesses before your customer finds them. So again, we want to do everything we can to add cumulative stress to the product. So someone may be asking, well, do we use a different product for each step in the process? Actually, if we don't have to, we won't. We'd like to take one product, subject it to the entire process, not make any changes to the unit under test until we get through the final stage in the process, if possible. Now again, some of the things that we incorporate with HALT testing or the HALT process is first functional testing and monitoring. We don't just place the unit in the chamber, set it, and forget it. No, we take the unit, we monitor the unit. Functional testing is performed throughout the process. The sixth degree of freedom vibration is incorporated in the process. Product-specific stresses, as I said before, voltage, frequency, margining, and anything else that would add stresses to the product. The HALT process is a 4-step process that starts with a thermal step stress. Thermal step stress, we start with the least destructive test or least destructive process first, because once we get to vibration, there's a potential for dislodging components and so forth. So we start with the least destructive of all the steps first, and that is the cold thermal step, which starts at 25 degrees C or 20 degrees C and then steps down in 10 degrees C increments until we reach the operating limit for the product or until we reach the limits for the chamber. The chamber can go as low as minus 100 degrees C. And on the hot side, the step stress process is started at 30 degrees C and ramped up in 10 degree steps after the dwell, of course. And then it's stepped up until we reach the operating limit again for the product, or we max out the chamber limit, which is 200 degrees C, which most units will probably be frying at that point. So we wouldn't probably go that high. We would use engineering judgment. So once the product started melting, then of course we would back off, because we don't want a puddle of wax when you go back to your test site. And then vibration step would start at 5 GRMS, a random vibration, and it would step up in 5G increments. The limits that we find, the operating limits that we find with cold and hot step stress would be used for the rapid thermal transition. The temperature extremes that we find would be used for rapid thermal cycles, and the product would undergo about 5 temperature cycles with a ramp rate of about 60 degrees C per minute from the hot and cold operating limits that we found. And then the vibration limit that we found, we would use that combined with the rapid thermal transition cycles for the final process, for the final step in the process, which is the combined environment. Now, when failures occur during HALT, again, we should not discount anything. We should not ignore anything. We should not say, oh, well, that the product was tested far outside of the limits. It will never see those extremes. Well, that would not be very wise to discount any failures found outside of the extremes, because over the product's life, the same failures found at extremes may be found under normal conditions. But we're finding them a lot quicker with the extremes. So HALT, again, is a closed-loop process. Once a failure is found, then the root cause should be found for the failure. Some kind of analysis should be conducted at the customer site or on-site if possible, because with HALT, we generally ask that someone who is familiar with the product be present during the process so that they can help to troubleshoot the product and troubleshoot those failures found during the process. And the MET engineer or the HALT engineer would be instrumental in providing feedback about the chamber and other ancillary questions about the chamber operation and so forth, but not necessarily about the product, because you're going to be more familiar with your product than the personnel at the test site. So if design changes are implemented based on the results found in HALT, then again, a verification HALT should be conducted as well. Now, the key, again, to an effective test is to find the root cause for any failure. Otherwise, you won't be taking full advantage of the process. I like to use this slide, and some of you may have seen it, but this pie chart it really does give everyone a good understanding of every step in the process. It shows that if we eliminate one step in the process, then we are foregoing an opportunity to find failures that may be the cause for all the warranty issues or the returns. So if you eliminate any step in the process, you could potentially be missing some information that could save your company a lot of time, energy, and money. So every step in the process is important, from the temperature extremes with the 60 degrees C per minute change in temperature to the high temperatures up to as high as 200 degrees C on a product, low temperatures testing down to as low as minus 100 degrees C, combined environment of temperature extremes plus vibration, or just vibration standalone. So every step in the process is important, and none of those should be ignored, nor should any of the failures found with any of the steps be ignored. Some of the common failures that have been found are listed, and again, this list is not all-inclusive, but it does kind of give you a good snapshot of some things that may have caused problems for design engineers in the past, may have caused you some problems. I'm not sure, because I'm not sure who's on the line. But the failures found: cold solder joints, nicked sleeves, components out of tolerance, drift, you name it. So HALT has been successful in finding many of the failures listed here. I like to include a test case for people who may still be on the fence or still not sure if the process is what we claim it is. And we do believe that the process is very valuable to every design engineer or every manufacturer. Honestly, it is a tool that I would not eliminate or exclude from my toolbox. So basically, a product was a battery charger, and the company they needed to resolve an issue rather quickly for a serious issue that they were finding in the field. So they had units that were being returned, and customers were complaining that these battery chargers were having intermittent issues, intermittent failures. What the company shared with us was that the product was being manufactured, and then they found a cheaper way to manufacture the product, so they went to another factory. Well, the new factory changed the soldering process, and the customer started getting warranty returns. So the customer wanted to fix the problem and was pressed for time and wanted to know if the failures could be duplicated during HALT. And one test is worth 1,000 expert opinions, so we said, bring it in. We tested the product, and we were able to provide the customer with the results that they were looking for. So what we found was that what we did, we just tested the units side by side. So we took a dozen samples, more than a dozen actually, and we took the samples with the questionable solder, and we took the ones from the original process. And both samples were tested side by side. A fair amount of both samples were tested side by side. And what we found was that down to minus 50 degrees C from ambient, both products operated with no anomalies found. However, when the temperature reached minus 60 degrees C, one of the units stopped functioning, and the other unit began operating erratically, but that unit fully recovered at ambient. Again, with HALT, we don't just stop there. We take the troubles found, those units, and those are returned to the manufacturer or returned to the customer. So the onus is on the customer to do a root cause analysis. And what the customer found after they took the products that failed, or the ones that had issues in the lab, once they took them back, you can see sample 1, they found that a Hall sensor was the cause of the failure. And then sample 2, they couldn't find anything with that unit or those units. So after their final analysis, they discovered that the units with the questionable solder, they had 10 whiskers, and that was the reason for all the returns. So what they were able to do in less than a week was find the same issues that their customers were finding, and you see in the previous slide that the failure was found at minus 50 degrees C, which I'm pretty sure is not the operating limit for that product. And some of you may be in agreement or nodding your head, and some of you may be just baffled by all the information. But what we see is that the issue was found in a relatively short amount of time and gave the customer the confidence that they needed to make a decision about where to have the product manufactured. And another test case for so corrective action was they discontinued production at the manufacturing facility with the new solder and used the manufacturer with the no solder process issues. Pretty simple fix that was found in less than a week. Now the second case, and the last one for the purposes of this webinar, HALT was applied to an electric meter. Now, this meter was under constant revision, but the customer was a believer, and the customer had incorporated HALT into their manufacturing and design sequences. So what the customer found was that by introducing HALT, each time the product was changed, they would find if the product change was valuable or invaluable. So they would basically subject the unit to HALT after each revision. They wanted to determine if the previous or the new revision resulted in a more robust product. So what they did was on their newest release, Rev 3 of the product, they tested it side by side with the previous Rev 2, and they were tested simultaneously. Both products were fully operational, but the problem was found during, or problem was detected during vibration. From 5 GRMS to about 20 GRMS, no anomalies were noted. However, at 30 GRMS, the unit Rev 2 lost power and didn't recover after power cycle. However, the new unit, there were no anomalies found. So the customer, as we said several times in this webinar, that a root cause analysis should be done, find out why the product failed, and determine whether or not the failure needs to, some corrective action needs to be implemented. But in this case, they were just doing a comparison because a new release of the product is on the market, and they just wanted the confidence in the product. So what they found on the visual inspection was that 2 capacitors were dislodged on the unit. However, on the new unit, there were no anomalies. So corrective action, there really was no corrective action, but the customer was confident that the new unit was more robust than the previous one. And that customer continues to incorporate the HALT process for all new products and for revisions of existing products. So if you have heard something that will make you incorporate the process in your program, then what you need to understand before preparing for it is some questions that we ask and some things that you can do on your end to ensure that when you do finally come into the lab for testing, that you are equipped with the information, the number of products needed, and everything that will help give you confidence in the whole process and to help you make the most of your time and test effectively once you are here. So we determine what engineers need to be present based on who you have available. So you let us know, and then we can give recommendations, or we can try to complete the process without your engineers, but then again, it saves time when someone who is familiar with the product is present during the process. Again, list major functions of the unit. The goal is to test 100% of the functions of the unit. You don't want to forego any of the unit's functions or discount anything on the unit. You want to get as much information as possible about your product while you are in the lab. And you should list the methods of measuring functions, determine what equipment is required for measuring those functions. Do you need an oscilloscope? Do you need a data logger, a multimeter? Whatever is required, then that equipment should be discussed, and it should be determined who will provide that equipment up front. Determine what is pass or fail. Pass or fail can't be red light, green light, because that will not really give you confidence in your product if you can't see the red light or the green light. So we need a more detailed or a more in-depth way of monitoring the product while it's under test. So those kinds of things are discussed before you even come to the lab. So rather than looking at a red light or green light, maybe we can connect leads to the product, a digital voltmeter or an oscilloscope or something to monitor critical nodes, and perhaps some other method of monitoring or acquiring data while the product is under test. How will the unit be operated while it's in the chamber? So if there is a variable power supply that's needed, what is needed to support the unit under test? What kind of support equipment is needed? Determine if there is any shutdown circuitry. Are there any thermal bypass circuits? Anything that we can do to continue testing beyond the normal limits is what is optimal in the HALT process. How many units will be tested at a time? If the unit is relatively small, or if many units are available for testing, then you can decide how many, but we generally recommend 3 to 6 samples. How many spares are available, or if spare parts or sub-assemblies are available if we're testing at a higher level of the unit. All of these issues would be discussed and ironed out before coming into the lab. Are all the units of the same revision level? Unless you are doing a comparison test, you would want to have all revisions the same during the HALT process. Unless, like with one of the examples I'm shown previously, unless you're doing a comparative analysis. What special cables are required? For the access port, from the access port to the test bench, we need at least 5 feet of any type of cable from the product to the test bench or to the support equipment outside of the chamber. We also talk about if sensitive nodes or modules can be isolated and located outside of the chamber. And when I say that, I'm really talking about LCD displays or hard disk drives, anything that is not actually being tested with the product that can be located outside of the chamber. That would be very helpful. And also, if a non-functional sample is available, then that would help to iron out any fixturing issues before coming into the lab. While fixture design is really never never really poses an issue during HALT because fixturing is relatively simple and straightforward. There are no heavy fixtures, and as you would find in electrodynamic vibration tests. So you wouldn't use the same type of fixturing for HALT. You would use lightweight aluminum, extruded rod, some other fixturing that is relatively simple, lightweight, and inexpensive. So as you can see, when preparing for HALT, there are quite a few things to consider. I think I've covered most of them here. But if you had some others that maybe I didn't cover, I'd be happy to discuss those. So the HALT process, is it good? I would say so. The process, again, is simulating the product, not simulating any environment. What we're looking to do is to test the product outside of its normal limits to find any weaknesses before the product goes to market. If the product goes to market after undergoing HALT, hopefully with the HALT process you will have the confidence that you have released a more robust product to the market. The out-of-box quality will be better than if you had chosen not to incorporate the process, and the product could potentially reach the market sooner rather than later with the incorporation of the process. But preparation is the key, and it will help to ensure that the process is efficient and effective. Are there any questions?
So that concludes the presentation portion of the webinar. Tomorrow, an archived copy of the webinar will be available on metlabs.com, and we will send an email with a link to this file. Now we're going to answer questions. If you have any questions, please type it in the questions area of your control panel. And for questions that we can easily address now, we'll read them aloud and then give the answer.
There's a question that reads, do we need to disable the protection inside the product while performing HALT? The answer is yes. Any nodes that can be bypassed, any thermal shutoffs that can be bypassed, first we want to ensure that the thermal shutoffs will actually do what they're intended to do, but then if possible, we would like to disable those and test beyond those limits to, again, find problems with the design or find any flaws outside of the normal limits of those shutoffs. There's another question, what if a product doesn't fail at 60 degrees C? I'm not sure if I understand that question, but I think it's basically asking if 60 degrees C is the limit for testing, and I would say that there are no limits with HALT unless we reach the chamber, the thermal limits of the chamber, and or the destruct limits for the product. There's another question on the temperature test from the cold temperature at first instead to start from room temperature and then going down in temperature. The answer is on the cold thermostatic stress, the temperature chamber is started at 20 degrees C and is ramped down in 10 degrees C increments to the lower operation and or destruct limit for the product, or the lowest operating temperature of the chamber, which is minus 100 degrees C. Then on the hot side, the hot thermostat stress, the testing would start at 30 degrees C and then ramp up to the operating and or destruct limits for the product and or the upper operating limit of the test chamber, which is 200 degrees C, which is not very likely for many products. There's another question. If my product is very big, can we do HALT on a subassembly? Is there any advantage or disadvantage? Well, the answer to that question is there are no limits to what can be subjected to the HALT process. The HALT process can be tested on the circuit board up to a total total assembly of a unit. So it can be broken down into smaller subsections, if you will. Someone asked the question, what is the cost for HALT testing, daily, weekly, or by product? Testing is usually a daily rate, and we have sales personnel on staff that would be happy to provide you a quote. There's another question. Do we have to be present during testing, or is MET staff only doing testing? Well, we recommend that a person who is familiar with the design of your product be present during testing, but it's not absolutely necessary. MET staff has been successful in conducting the HALT process on products without the customer being present. It just requires more documentation on the MET engineer's part, but root cause analysis and help with troubleshooting can definitely be increased if someone who is familiar with the design is present during testing.
So if you have any additional unanswered questions, please contact us via phone or email. Tomorrow we will send a follow-up email that will include a link to the presentation. That concludes our webinar, and thank you for joining us.